So the title of the talk is about frontiers of efficient learnability for neural networks. And the question that I'm really interested in, here I've highlighted, is what is the richest or most expressive class of neural networks that we can come up with provably polynomial time learning algorithms for in a distribution-free setting? And one of the main results that I'll talk about in this talk is the first efficient algorithm for learning neural networks that have two nonlinear layers. There's been a lot of work done for the case where you have one nonlinear layer, and I'll properly define this later. And this is based on a Colt 2019 paper with my PhD student, Surbi Goel. In addition to this being sort of a natural question from a theoretical computer science standpoint, what's the most interesting class of neural networks that we can provably learn? The real kind of long-term goal of this line of research is to come up with new algorithms for learning neural networks, hopefully at some point deep neural networks. If you think that backpropagation is the end-all be-all, the last word on algorithms for training neural networks, this talk probably isn't for you. But I'm optimistic that there are more powerful algorithms out there for training neural networks. And as I said, the long-term goal is to find them. So we'll have to start with sort of simpler, shallower networks and hopefully build from there. But this talk is about sort of what we can hope for in the hardest case, or one of the hardest cases, when you're not making any assumptions about the distribution. OK, so to describe the actual statement of the results, let me tell you about two models of learning that I'm going to work in for most of the talk. And the first is sort of what I would say is, I would call this the agnostic model of learning. And the setup is as follows. You have script C, which is the class of neural networks that you want to learn. If you're familiar with, some of you may be familiar with this teacher network, student network model. So these are going to be the teacher networks. And we're going to have a distribution D. It's going to be an arbitrary distribution for right now. And then we're going to define this quantity opt, which is basically the square loss of the best fitting neural network in your class C with respect to D. So I'm going to be looking at square loss. It's the expectation with respect to a draw from D of C of x minus y. Y is the label. And your opt is defined to be the minimum over all C in your function class. And the goal is to output some h, some efficiently computable or polynomial time computable h, whose square loss with respect to this distribution is competitive with opt. So the true square loss of h with respect to this distribution should be opt plus epsilon. Okay, are there any questions about this model? So notice that when opt is 0, it means that there is some neural network in your function class that perfectly labels all of your data. And that would sort of correspond to these traditional pack models of learning. Here we're going to consider a model where there could be some noise, and you just want to be competitive with the best fitting network in your class. OK, and then perhaps a slightly less well-known model that I'll be considering, but it's important for the purposes of this talk, is something called the p-concept model. This was defined by Kearns and Shapiri in '94.
Isn't that regression?
Yes, it basically is a model of regression.
C of x is called the regression function.
Yes, the C of x is called the regression function. Yep. And their only their only spin on it was to basically put a polynomial time computable framework around everything. So yeah.
So is y deterministic after you know x for this distribution D?
No, C is the conditional mean function. So you could think of y as C of x plus some mean zero noise. And the goal in this case is to really estimate the conditional mean function, come up with some h, that's close to the true conditional mean function with respect to square loss. So it's an easier model than the agnostic model because the noise is somewhat structured here in the sense that it's mean 0. OK, good. So what can we hope for, given these sort of models of learning? Well, unfortunately, it turns out that this agnostic model of learning is quite hard. So for arbitrary distributions, it turns out that agnostically learning even one ReLU, so being competitive with the best fitting ReLU for an arbitrary distribution, turns out to be computationally hard. It's unfortunate, but yeah, even learning one ReLU in the agnostic model is hard. We'd like to learn slightly more interesting neural networks. So
when you say one ReLU, you mean one hidden unit?
Literally one ReLU. So I'll talk about it later, but literally.
Like ReLU of a linear thing.
Yeah, ReLU of w dot x. That, as you vary over weight vectors w. So agnostic. So coming up with some w prime that's competitive with the best fitting ReLU of w dot x turns out to be computationally hard. And the distribution that you need to work with there is a discrete distribution so that you can encode these parity with noise problems. OK, so our solution is going to be to switch to the p-concept model. So it's still going to be distribution free, but there's slightly more structure in the sense that the noise is mean 0. And I will talk about the case that a lot of people have analyzed where the marginal distribution is Gaussian. There are many papers for learning simple models of neural networks when the marginal is Gaussian, but I'll get to that later. But right now, I don't want to make a Gaussian assumption. And I should also say, just for clarity, because there have been a lot of works that give algorithms for achieving low training error, that the goal here is not just to achieve small training error. It's really to do learning in the sense that we'll be achieving small test error. OK, so I can just state our main result for 2 nonlinear layers. And I think this is the most interesting statement or instantiation of our results. We have sort of a general framework. But I'm going to let sigma be the sigmoid activation. And then U can be any monotone Lipschitz activation. So ReLU, for example, will fall into this category. But anything that's both monotone and Lipschitz. And then I'm going to have, let's say, k hidden weight vectors, w1 through wk. And I will need that the 2 norm of each of these hidden weight vectors is at most 1. That is crucial. And as I said, we're working in this p-concept model. So I'm going to assume that the conditional mean function is of the form u, so this outer nonlinear activation, applied to one hidden layer neural network. So you have these aj's that are these unknown coefficients. And then you have these, as I said, wj's that are unknown hidden weight vectors. OK, so if I didn't have this u nonlinearity, there's even some controversy as to whether that's a 2-layer or one hidden layer neural network. Since I have this nonlinear activation on the outside, I prefer to call these 2 nonlinear layer neural networks. Some people actually call these depth 3 neural networks. It's not totally standardized. But this is the function class that we're going to give an algorithm to learn. And our algorithm works for any distribution on the unit sphere or the unit ball. Okay, and when I say it runs in polynomial time and sample complexity, I mean in all the parameters that we have available to us. So it will run in polynomial time in k, epsilon, the error parameter, the 1 norm of a when viewed as a vector. If the range of y is in some interval 0m, it will run in polynomial time in m. Yeah, that's so this is the statement of the results. No other assumptions.
Is it important that it's sigmoid and let's say not another layer of ReLUs?
Yeah, good. So I'm going to get to that. I wish I could have this layer be ReLUs, but you run into again computational hardness results if you do that. So yes, it must be sigmoid.
If it was a ReLU, that would be a special case. That would be a generalization of the special case, which is hard, as you said earlier.
No. So we switched to the p-concept model. So it was hard in the agnostic model. One ReLU was hard in the agnostic model. Here I've made the model a little bit easier. The noise is structured. So it is reasonable, and maybe I have this. Oh yeah, so I'll just say, it's a good question, why am I talking about sigmoids here? Maybe you could hope for ReLUs. So it turns out that in sort of any direction that you would like to push this result for a distribution-free result, like if you wanted ReLUs instead of sigmoids, it turns out even in this p-concept model, the problem becomes computationally hard. If you want sigmoids with, say, like very large slope so that they begin to approximate, like a threshold activation, it becomes computationally hard. Let's say that you wanted, so this has one nonlinear output activation. Let's say you wanted to do the sum of two nonlinear, t nonlinear output activations. That's a possibility, but it has to scale exponentially with t in that case. So again, you lose the polynomial scaling and all the parameters. You can prove that's computationally hard. So you might say, well, can you relax this notion that the 2 norm of w has to be bounded by 1? No, then the problem becomes computationally hard. So in sort of any way that you want to push this, yeah. Yeah, so I'll describe sort of what we can do in a minute, but I feel like this is the best instantiation of our result. Yeah.
Do you have like a general characterization of when it's easy and when it's hard?
Yeah, I'm going to talk about that.
And what do you need about the sigmoid? Do you need that it's just smooth and bounded?
So if its slope is L, sigmoids can have various slopes. If the slope is L, then you have to pay exponentially in the slope.
Okay.
Yeah.
But I could do something which is like non-differentiable, for example?
Yes. Well, no. Non-differentiable, yes, you can do. I'll describe what we can do in a second. OK, so to describe how our result works, it does use some basic kernel methods. So let me just have one slide on sort of the basic kernel methods that we're going to use. I'm going to let k be a kernel function or a similarity function. So I'm assuming sort of a basic working knowledge of reproducing kernel Hilbert spaces. But if you don't know it, it's OK. You can just think of k as some sort of similarity function. H is a Hilbert space. And then corresponding to our kernel function k, there's always a feature map that takes x and maps it into this Hilbert space H. And then the kernel function has the nice property that kernel of x prime is equal to the inner product of phi of x prime. OK, so I will be embedding things into an RKHS. And then I'm going to say that a function f is epsilon b approximated by a kernel if for this function f there exists a vector v in your Hilbert space so that f of x can sort of be computed by v in the sense that for all x, f of x minus v inner product phi of x is absolute value is going to be at most epsilon. And the b is going to come into play in the sense that the 2 norm of v squared is going to be less than or equal to b. So this is an epsilon b approximation of f. Yeah.
2 norm here means L 2 norm.
Yeah.
Not B.
Yeah, no, we could use that norm, but here it's just going to be 2 norm. OK, so I think in retrospect, the following is sort of a natural approach. Remember, we wanted to sort of find a function that approximately minimizes this square loss over all the neural networks in your class. So one thing you could try and do is just prove that for every C in your circuit class or your neural network class, it is epsilon b approximated by some element in the Hilbert space. So you can take your neural network, you can embed it in your Hilbert space with some, by some approximator v that has 2 norm at most b. And then this problem of learning the neural network really does reduce to the following optimization problem. If you have this structural approximation, so let's assume that we know this is true for every neural network, we can embed it into the RKHS. Then this problem just becomes min over v in the RKHS turns out to be the empirical loss of v inner product phi xi with under the constraint that the 2 norm of v squared is at most b. Okay, so I'm just rewriting. We want to minimize square loss for our neural network. We just embed it in the RKHS and minimize over the RKHS. And then the representer theorem basically says that the optimal solution is equal to some like linear combination of phi of xi's. Okay, so it actually says it's in the span of the optimal solution to this problem is in the span of the xi's. And then you define this kernel matrix K, whose ijth entry is the kernel function applied to ki xj. And then this problem actually, so because we know that we only have to look in the span of the xi's, this optimization problem really reduces to something quite simple. It just reduces to min over alpha k alpha minus y with respect to the constraint that alpha transpose k alpha is at most b. OK, so this whole problem of learning the best fitting neural network, my point here is that the whole problem, these are trivial steps, but my whole point is that the problem of learning the best fitting neural network really corresponds to just a regression problem, just a kernel ridge regression problem with respect to the Hilbert space.
Isn't that alpha transpose alpha less than b? I mean, why do we have the k over the?
I
Because
think
you assume it's norm to a Euclidean norm squared, so it translates to alpha transpose alpha.
I think you need the kernel function in there, because that's what embeds it into the space. I mean, I don't know. I worked this out and wrote it down, and this is what I'm pretty certain this is the correct formulation. OK, so this seems like a reasonable approach. If I want to learn neural networks, just approximate them in some Hilbert space and do kernel ridge regression in the Hilbert space. I don't know, decent idea. And it turns out that so we did this a couple of years ago. And I think 6 months before we did it, Yuchen Zhang, Jason Lee, and Mike Jordan also did it. And our results are slightly different, but in some sense sort of the same. And what they did was they wanted to embed the richest class of neural networks that you can into this Hilbert space. And they needed this extra condition that their neural networks were sparse. And they used a type of polynomial kernel. And for some reason, there are no sort of quantitative bounds in their paper. But they do give the entire strategy for doing it. In our paper, we took the same approach, but we used this sort of notion of approximation instead of exact computation. I think the exact computation required them to take these sparsity assumptions. And we worked out quantitatively what happens. And it turns out that you can faithfully embed one hidden layer of sigmoids using a type of polynomial kernel into a Hilbert space of the RKHS corresponding to this multinomial kernel. OK, so the kernel function we actually used was k of xy is just the sum from I equals 1 to d for some parameter d of x inner product y raised to the power I. And why does this work? How did we prove this, that you could embed one hidden layer of sigmoids? Well, there's this lemma in this paper by Livni, Shalev, Schwartz, and Shamir that says any sigmoid can be approximated by a very low degree polynomial. And then there's a lemma of Cherstoff that basically says, he proved a lemma that basically said, low degree polynomials have bounds or correspond to bounds on the 2 norm of the polynomial. So you can basically combine these two lemmas and say that for the sigmoid function, it has a low-degree polynomial whose coefficients, the sum of the squares of the coefficients of that polynomial, are also kind of nicely behaved. And if you combine those two things and use this multinomial kernel, then you get that you can embed it into this Hilbert space and that the norm isn't too large. Okay, so it's a particular property of sigmoid that enables them to do this. And so you might ask, well, what happens if you want to do a ReLU? So if you want to do a ReLU, then it's sort of bad news. It turns out that ReLUs require both high degree and high weight in order to be faithfully embedded into an RKHS, in fact, any RKHS. Okay, so that's why, so in this paper, this was Colt, I guess, 2017. So in this paper, this is why we were able to agnostically learn one hidden layer of sigmoids, and then we weren't able to do anything else. We didn't understand why we couldn't do we couldn't do a ReLU, so there are these lower bounds structurally, but also we proved these hardness results saying any algorithm is going to fail. Yeah?
Can you explain a little more what the Scherstoff result says? I'm a little confused.
Yeah, it basically says if you have a polynomial over an interval of a certain degree, and the largest value that it takes on is m, then you can actually bound the sum of the squares of the polynomial. And that's, this complexity, the B, the norm in the Hilbert space, corresponds exactly to the sum of the squares of the coefficient. So you have these existential results, but you actually need to get a bound on the sum of the squares of the coefficients of that polynomial. And so this was the way that we got at it. Because you end up needing to use Rademacher complexity to prove a generalization bound, and that really, B is what controls that Rademacher complexity.
And to approximate sigmoid with low degree, there's no need to bound the slope?
Yeah, no, you do, yeah, the degree of the approximation depends on the slope. That's why you pay.
So low degree means, in what sense it's a low degree? That the slope is not too crazy?
It means if you want to approximate, yeah, so it's going to be exponential in the slope. So for a standard sigmoid of slope 1, 1 over 1 plus e to the minus z, you just get a actually get a logarithmic in epsilon approximation. If it's L in general, then the degree of the polynomial scales as L times log 1 over epsilon.
Oh, so it's linear in L. Okay.
It's linear. Well, the degree is linear in L, but then the 2 norm actually scales exponentially in the degree.
Yeah.
So you pay in that sense. Okay, so as I said, the party sort of ends here. I mean, this is as far as this approach will take you. I mean, you'd think, oh, maybe you can do one more sigmoid at the output, but you lose these approximation results. As we've talked about, you sort of can't do a single ReLU. So that's the end. And in fact, so these were kernel methods, but you may be familiar with other results that don't use kernel methods, but use SGD plus overparameterization to learn neural networks. For example, this is a very nice paper by Alan Zhu, Li, and Liang. And it's about learning neural networks where your student network, so what you're training, is a 2 or 3 layer neural network. That's your classifier that you're going to output. And that's what they do. And they have a very sophisticated analysis to show, for example, for a 3-layer network, that SGD will both achieve small training error, and it will have small test error for a class of neural networks. Okay? So then you might ask, well, what is the actual class of neural networks, the teacher class of neural networks? What is that class? What are they able to learn in this paper? And if you dig into the paper, they define these complexity measures. And these complexity measures, it turns out, if you parse them and already you have an activation, a smooth activation function phi, and they look at its Taylor expansion. And it turns out if you look at these complexity measures, what's going on is that the class of neural networks that they can learn really does correspond precisely to the function class of neural networks that these kernel methods learn. It's exactly this. In fact, it's slightly smaller for some technical reasons. But essentially, if you have a neural network that can be viewed as some polynomial, or composition of polynomials whose sum of squares is small, that's exactly the function class of neural networks that their techniques are able to capture. OK, so for kernel methods and for these methods that do SGD plus overparameterization, you sort of run up against the limitations of these RKHS approximations. OK, so our idea was to, as I said, the long-term goal of this research is to come up with new algorithms. So our idea was to use techniques from isotonic regression for various reasons that will become apparent. Okay, so let me say just a few things about isotonic regression. So I'm sure we're all familiar with the standard scenario of just linear regression, where your conditional mean function is just a linear function. Expectation of y given x is equal to w inner product x. And of course, you can solve this problem by ordinary least squares regression and figure out what the conditional mean function is. Very well studied problem. OK, so isotonic regression is a more difficult problem where the conditional mean function is actually some monotone function of w inner product x. And the monotone, it's some, let's just say it's some u of w inner product x. And for the purposes of this talk, u is going to be monotone in Lipschitz. OK, so it's just a generalization of linear regression to this harder case. And the goal is to find a w prime that's close to the conditional mean function. So you want to find w prime such that the expectation of u of w prime dot x minus u of w dot x squared is at most epsilon. And it turns out that this is it's not hard to see that this is actually a non-convex optimization problem for many choices of u. For example, rel u or sigmoid or whatnot. And somewhat surprisingly, although he's not here, the first efficient algorithm that I'm aware of for solving isotonic regression is due to Adam Kalai and Ravi Sastry. And they called their algorithm the Isotron algorithm. I think it was in Colt 2009 or 7, something like that, 8. And then there was a follow-up paper by Kakade, Kalai, Kanade, and Shamir, where they simplified their analysis and got it to really work in the right noise model. And they called it the GLM-tron, because these are also referred to as generalized linear models. OK, interesting.
Question?
Yeah.
So just to understand, so it hinges on the fact that you're in the well-specified case, basically, that you can solve this. Because you just told us.
Yes,
this.
Correct. Yeah, exactly. So we're in this p-concept model, this regression model, where you know your conditional mean function is equal to u of w dot x. Yeah. Yeah. Otherwise, you're in trouble. Although I will say a few things about that soon. OK, so it turns out that even though this looks like not that much more interesting than regular regression, it's a surprisingly powerful tool. And for example, Raghu, who's hiding behind the column, and I, when I was last at MIT, when I was here 2 years ago, we used algorithms for isotonic regression to come up with the first algorithms for doing structure learning for Ising models or higher order MRFs that have essentially optimal running time and sample complexity. We called it Sparsitron. Philippe thought it was all already known and trivial. What? Oh, OK. The MRF case? OK. Yeah, so it turns out it's a surprisingly powerful tool. And so the algorithm that we use for learning neural networks, there are all these trons flying around. We called it Alphatron. And here's the pseudocode. This is how we learn the neural network. OK, so we basically let k of x and y be the sum from I equals 1 to d, as I said, of x inner product y raised to the power I. So this is this kernel function. And you draw a training set. OK, and you initialize alpha to be 0. And then at iteration t, I have this classifier h of t, which is going to be u of this summation from I equals 1 to m, alpha I t, k xi x x xi. So this, if you ignored the u, this is sort of exactly the type of classifier that you would get if you sort of did kernel ridge regression. But instead, it's inside this u. But in order to fully specify the algorithm, all I have to do is indicate to you how to update these alpha i's, these weights. And this is the update rule. This is it. You just look at the previous alpha I, and you add lambda, which is like a step size parameter. M is your sample size that you've taken. And you multiply by the ith label y minus ht of xi. Okay, so this is the update rule for the alphas. And you just iterate this. And at some iteration, you will come up with a classifier that's epsilon close to the true conditional mean function, assuming that your circuit class satisfied, I had that slide that said when our algorithm works, basically assuming that it satisfies those conditions.
That's for you, that's the random here.
OK, yeah, good. So u can be any monotone Lipschitz activation. Yeah, so for example, yeah, you could take u to be ReLU. And then on the inside, you could take anything that can be embedded into an RKHS, for example, one layer of sigmoids. So you'll get ReLU of summation of AI sigmoids. Right.
You need Lipschitz assumption because Kalai's result needed.
Yes. You need u to be Lipschitz because these algorithms for isotonic regression require that. You'll see why. I'll talk about that in just a little bit. You'll see why later.
Just to understand, the Kalai's algorithm, it learns simultaneously the monotonic function and the weight, right? Because the monotonic function, if you want to learn directly, that's
so,
80s. That's
So their algorithm actually does more. You don't need to know the u, the monotone function, and they will learn the weight vectors. Yes,
okay.
Correct.
And that's where you need the Lipschitz function.
Yes.
And that's what they need the Lipschitz function.
Yes.
So is this a gradient descent? I mean, like it feels like it is, but
I'm gonna answer that in just a second.
Okay.
Okay, so just two. It's very similar to gradient descent, but I'll answer that in a second. It uses a straight through estimator. So 2 points that I wanted to make about this. First, we don't use, if you think about it, we don't use the representer theorem. And secondly, we don't regularize. So you might say there's some implicit regularization going on. The algorithm does not, unlike kernel ridge regression, there's no regularization going on, and we don't use the representer theorem. So it's a little mysterious that it works. Oh yeah, so here's my diagram. So these are provable results. Here's the frontier of efficient learnability. This is all hard. You have kernel methods. SGD plus overparameterization is about the same. And then Alphatron gets you pretty close. This is for distribution-free learning.
Sorry, what is the x-axis here?
Like, richness of function classes that you can learn by whatever measure. I didn't want to get into it. Next.
Guaranteed to converge Alphatron?
Yeah, guaranteed to converge. Yeah. OK. Let me give one application to computational learning theory. This is a classical problem. So another consequence of Alphatron is that you can basically take every PAC learning algorithm that you are familiar with, except for learning parodies, and that are known to work in the PAC model, and you can get them to work in the p-concept model, which was sort of the main goal of Kearns and Shapiri's original paper. So let's assume that we have a DNF formula, which is just an OR of ands. And right, so it's an OR of ands. And now all I have to do is sort of embed this very, very simple function, an and, into an RKHS, which you can do. Then what did I want to define u as? Oh, yeah. So then I wanted to define this function u such that u of 0 equals 0, and u of the interval like 1 over k to 1 is equal to 1. And then it linearly interpolates in between. So u kind of looks like it's 0, and then it shoots up to 1. So this is going to be my choice of u. And then Alphatron tells you sort of for free, you get to learn u of 1 over k times t1 plus tk, where the ti's were the terms. Okay, so now if you think about a DNF formula, if one of them is true, then your function should output 1. And if none of them are true, it should output 0. But that's exactly what u does. And the slope isn't so bad. The Lipschitz constant is k. So you run in time sort of polynomial in k. But that's OK. We were expecting to sort of run in that time anyway. Okay, so this, for example, let's say that you had a scenario where y was a Boolean label, 0, 1. And the probability that y equals 1 conditioned on x is equal to, say, the number of terms satisfied by x in the unknown DNF. So this is this sort of is a natural learning problem. You see this Boolean variable 0, 1, and the probability that it's 1 is exactly the fraction of terms in some unknown DNF formula that are set to true by that x. So those are the examples that you see, and you'd like to figure out what was the unknown DNF formula. You can get close to it with respect to square loss if you run Alphatron on it. If you want strict polynomial time learnability, then the learner needs query access. But I guess my point is that typically for learning these types of Boolean function classes, they're sort of very complicated analyses. And here, we just need to take the basic building block, which is an and, embed it, and then Alphatron, with your simple choice of u, Alphatron sort of gives you the result for free. OK, so getting to Philippe's question about SGD, let me talk about how you can use isotonic regression. We've been talking about neural networks with 2 nonlinear layers. Let me talk about how you would learn 1 convolutional layer. And this is joint work with Serbi Goel, my student, and also Raghu. So in the convolutional model, you have one hidden convolutional layer. You have an input x, and you have these patches, which are in lavender. And you have an output function here, which I'm calling f of w. And it just takes there's one hidden weight vector w. It applies it to all of these patches of x, sends it through a nonlinearity. In this case, it'll be ReLU. It will be ReLU. And then you do average pooling here. So you just take an average. And the goal, given random samples from this network, is to recover w. OK, so if you ran SGD, what would you do? You would draw an example from your distribution. You would form this gradient that I've called g of t. So this is the gradient. And then you would just update per the step size parameter. This is your standard SGD approach. Our algorithm, which we call Computational, takes SGD, sets this sigma prime term to 1, and does the exact same thing. Okay, so it's basically taking SGD and just forcing the derivative of your activation to always be 1 at every step. And that's basically, that's sort of the relationship between SGD and these isotonic regression results. You're always forcing the derivative to be 1.
So it's kind of like taking an identity activation.
Yeah, it's called a straight-through estimator in the literature.
In what literature?
The neural network literature. I think who coined?
That people use in
Yeah,
optimization?
it's a trick that people use in neural networks. Like, for example, Bengio had a paper where they wanted to train neural networks with sign activation. It's not differentiable, and so he basically just said, oh, when you do the back prop, just set that to be 1. In some cases, that works. So when does our algorithm work? It works whenever the distribution is symmetric. So it could be Gaussian, uniform on a discrete set, a non-spherical Gaussian. We also work for any overlapping patch structure. And if the patch structure are these classical ones from computer vision where it's just a patch and stride in 1 or 2 Ds, then we only pay a constant factor overhead. And prior to our work, there were several papers that analyzed SGD. And to get the SGD analysis to work, it was, number 1, complicated. And number 2, required a bunch of strong assumptions. For example, your distribution had to be spherically Gaussian, and the patches had to be disjoint, so no overlap on your patches. So one of the points I'm trying to make here is that in terms of our understanding of neural networks, when you analyze SGD, you end up frequently with very complicated analyses. So if we want to understand deeper networks, it would be it's nicer, I think, to have these analyses that are sort of simpler for simpler networks. And I would argue that using isotonic regression just results in a much simpler analysis than looking at SGD. We also implemented this on some shallow networks, and Convolutional definitely outperforms SGD. You really have to, if you want to get SGD to work, you really have to tune the learning rate parameter very, very carefully. OK, so let me spend just a few minutes talking about what's going on here. What's the magic behind isotonic regression? Why does it work? And remember, we're in this scenario where we know something about the conditional mean function, namely it's u of w star dot x for some monotone Lipschitz u. So I'm going to define this loss and refer to it as the surrogate loss for the rest of the talk. So it's a loss. It's just a loss. And the loss of your current weight vector w at point x and y, I'm just going to define to be the integral from 0 to w dot x of u of z minus y dz. Okay, that's the surrogate loss. So if you take the derivative of the surrogate loss, you get this, u of w dot x minus y times x. You get a pretty simple expression. And then if you look at the Hessian of this surrogate loss, you get u prime of w dot x, xx transpose. And remember, u is monotone, so u prime of w dot x is always positive. Therefore, the loss is convex, because the Hessian is PSD. So great, it's actually a convex loss. That's nice to know. And the other, one other very nice property of this surrogate loss is that when you're in this p-concept model, the difference between the surrogate loss at some hidden weight vector w, I don't know why I'm reaching over. I can just write on the screen. W, minus w star, which is the best fitting weight vector, actually upper bounds the square loss, which is what we were interested in minimizing in the first place. Okay, so it turns out that minimizing the surrogate loss actually corresponds to minimizing the square loss. And these few properties of the surrogate loss that I've mentioned, I didn't know this, but they were actually known to Manfred Warmuth, who 20 or 25 years ago had written a paper about matching losses and had discussed some of these properties.
Sorry, is it clear that W star minimizes L?
Yes, because it's
Or expectation of L?
Yeah, well, it's always upper bounded. It's always upper expectation. Expectation it minimizes. Yes. Okay, so good. So now let's move away from this p-concept model where everything was really nice and assume we're sort of in a more general model. But I want to make the assumption that the surrogate loss, instead of being convex, is strictly convex, which for many cases it will be. But in the case when the loss is strictly convex, it means that if you minimize the surrogate loss, then the minimizer that you find has the property that the gradient is also 0 at that point. Okay, and if you recall, we said that the gradient of the surrogate loss was this u of w dot x minus y times x. This was the gradient of the surrogate loss. And now I'm saying at the minimum, the gradient is 0. This means that the expectation of u of w dot x at the minimizer is actually equal to expectation of y dot x, y times x. And on the left-hand side, these are referred to as, or these are known in theoretical computer science as the Chow parameters for your function u. They're the degree 1. If x were Gaussian, it would be the degree 1 Hermite coefficients. And on the right-hand side, you have sort of what I would call just the first moment. So I'm referring to the Chow parameters as chi w, and the first moment is chi y, sort of the Chow parameters with respect to y. So my point here is that minimizing the surrogate loss results in a situation where you're finding a w such that the Chow parameters of your activation function u match up with the first moment. Okay, so the last sort of result that I want to tell you about is just the simple case of ReLU regression, this time back in that agnostic model where we said everything was really hard. Instead, I'm going to come up with an approximation algorithm for you. Okay, so just remember, we have this distribution D. I want to find a weight vector W such that the expectation of sigma w dot x minus y squared is most opt plus epsilon. You're competitive with the best single ReLU on your distribution. And again, we're back in this harder, noisy model. OK, so as I mentioned, so the algorithm here is going to be just minimize that surrogate loss. You can use projected gradient descent, whatever you'd like. Find a W that minimizes the surrogate loss. And assume that your loss is strictly convex. Then you're going to end up in a scenario where you've matched Chow parameters. And what you can prove is that the W that you find, the Chow parameters corresponding to the W that you find when you minimize the surrogate loss minus the Chow parameters of the optimal weight vector are actually very close. I mean, they're at most opt plus epsilon. And in the simple case where your distribution D is Gaussian, where the marginal distribution is Gaussian, the Chow parameters with respect to W are actually parallel to W. Okay, the difference between the Chow parameters is actually up to constant the difference between the two hidden weight vectors. So I can just minimize my surrogate loss, find a W, and it turns out that this W is going to have overall error that's within some constant factor times opt plus epsilon. Okay, and we lose a constant factor here, and actually for technical reasons some other place, but you lose a constant factor, but you still get, so instead of getting opt plus epsilon, you get order opt plus epsilon. And then you can actually prove something else, and that is for more general distributions, for example, for log concave distributions, you can prove that the loss is strictly convex. And furthermore, you can prove that although the Chow parameters are not parallel to the weight vectors, the norm of the differences of the Chow parameters are up to constants the norm of the differences of the weight vectors. Okay, so even for log concave distributions, you can minimize the surrogate loss, and you can find a weight vector whose error is at most opt plus epsilon. This is some ongoing joint work with Ilya Stakanikolas, Serbi, my other student Sushrut, and Mahdi Sultanoktabi. And then just one last bookend to this particular result. We have an upcoming paper in Europe's that says, remember I said learning a ReLU in the agnostic setting is hard, but even in the case where the marginal distribution is a spherical Gaussian, so you might think, oh, well, in the case when things are Gaussian, it shouldn't be so bad. Maybe you can do something. Maybe you can get opt plus epsilon. It turns out that ReLU regression in that setting, no, actually is hard. It requires something that's super polynomial in the dimension to solve. And you can prove unconditionally that gradient descent will fail to find the global minimizer for ReLU regression, even in the case when the distribution is super well behaved and the marginals are Gaussian. So getting 1 times opt plus epsilon is hard. And that's sort of why on these, when you minimize the surrogate loss, even when the distribution is Gaussian, you still have to settle for these constant factor approximations to opt.
So when you say ReLU regression, you're talking about the one where you want to approximate opt, right? And,
Yes.
And your error is not, opt is not 0.
Correct.
Okay.
Yeah. So I'll stop here. Thank you.